Thanks a lot for organizing the workshop and for giving me the chance to present something. I'm very happy to be here. So today I will talk a lot about cosmology and not so much about string theory, but the reason is that cosmology is getting extremely exciting, so I hope to get you excited as well about it. In the end of the talk, I will talk very briefly about these two papers which connect to string theory, and yeah, there's also some work in progress. Okay, so the topic of the talk is dark energy. So as you know, our universe is expanding, not only this, but currently it's actually expanding faster and faster, so the expansion is accelerating. And this accelerated expansion is due to something we call dark energy, which represents 70% of the budget of energy budget of our universe, so it's not nothing. And the main question is, what is the nature of this dark energy? So we're going to investigate this question in the talk. And the nature of dark energy is actually characterized by something which is called the equation of state parameter W. And I'm going to spend 20 minutes talking about this W. So this is really a crucial quantity. So as you probably remember, radiation, or more generally relativistic matter, gives you a W of 1/3. And non-relativistic stuff, or matter, is W equals 0. Dark energy is none of this, because already from the theory, we can infer that if you want something which gives you acceleration, you need W smaller than -1/3 divided by this 70% quantity, which is roughly minus 0.5. So already you see that W is negative, which says that it's not one of those stuff. And so it has to be something else, which we don't really understand. So there are several options on the table for what it is. And one is this cosmological constant, positive cosmological constant, which gives you W equal -1. But another exciting option is that the thing is not constant. It actually varies with time. And then we call it dynamical dark energy. And one realization of this is quintessence. And this gives you W between -1 and 1. Of course, today it still has to obey this bound here, but in general, the W in that case varies with time. So we'll see how this varies. And again, let me stress that this is a very timely question because of the observations. So this year, we had the chance to have the results of DES and another set of results by DESI, which put constraints on these matters. And in the coming years, we're going to have, in addition, Euclid and this LSST. And so all these questions are going to be settled very soon, at least to some extent, but we're going to learn a lot about this in the coming years. So that's why I think this is exciting, and we should all know about this. Yeah, so I'm gonna present this. Yeah. So the thing is that in cosmology with observations, you have to put as an input a model to interpret your data. So it's not that you extract the model from the data, it's that you test the models one by one. So DESI says that lambda CM model, lambda meaning with a cosmological constant, is okay with observation with W equal -1. And another possible option, which is also okay, is dynamical dark energy. So this type of model I will talk about, which gives you W about -0.7, -0.8. I'll come back to this value. So for now, the two options are possible. Yeah. This is the central value, and there's some error bar around it that I'm not displaying here. The error bar excludes lambda CDM, to answer the question. I'm not sure exactly of the value, but yeah. Yeah, so, I mean, the class of model we're going to discuss together, yeah. The criticism on the data, I don't have much to say. Of course, this is more of an observational matter. But, okay. So, I mean, we should be aware of this. I think we should not ignore this. This is important. Okay, so how do we get there? So let's start with cosmology, cosmological model, before going to string theory. So the cosmological model we want to use is a scalar minimally coupled to gravity with a scalar potential. And we should not forget that we should also add some matter to this model. For most of the talk, I just consider one scalar canonically normalized for simplicity. In addition to this, we take the FLRW metric, which, as you all know, has the scale factor A. And finally, we take the field to depend only on time. So with this type of model, the W for dark energy is given by this ratio here. So as you can see, it involves the kinetic energy and the scalar potential in a certain combination. And that's what we're interested in. You can already see from this formula that this can be between -1 and 1. So, but what you have to do is, I mean, I give you a formula, but what you actually have to do is to go and solve the equations of motion. So solve the two-Friedman equation and the scalar equation of motion, and then you get a certain solution describing the history of your universe, right? So the history of A and the history of the scalar field. So you got some solution, and this you plug in here, and this gives you an evolution for this W. That's how you do this. So we're going to do this together. Let's check already a few solutions that we know very well. The first solution we know is the de Sitter solution in this model. The de Sitter solution in that framework is simply that you sit at an extremum, a minimum or a maximum of a scalar potential. And so at least classically, your field does not move, and so the potential is constant. And in that case, you get a cosmological constant. And from this formula, you get W equal -1. Another option is that you're not at an extremum of a scalar potential. You're on the slope of the scalar potential. In that case, you gain some kinetic energy. So both the kinetic energy and the potential are varying. And so W is varying with time. Right? So these are the two types of solutions. As we'll see, the variation is not arbitrary. There's quite some pattern in it. So you take one of the solutions, you plot your W, and then you compare this to the observations. That's what we should do. Good, so that's cosmology. So can we now do this within string theory? That's what we would like to do. So I think the first thing which should be stressed is that from string theory, there's a good thing for us, which is it's very easy to obtain a theory like this, right? And so from a string theory perspective, we have a natural origin to the dark energy, and this I think we should not forget. Dark energy for us is due to extra dimensions and some physical content in it. This is where dark energy comes from. This generates the scalar potential. That's a good explanation. Of course, the problem with this is that we should get exactly the right scalar potential to match with the observational constraints, or rather, the right scalar potential, which gives you the good solution, which match with observational constraints. But still, this is a good starting point. Let me still add two loopholes to this. We should not forget that we need matter, and getting matter together with this is difficult in string theory, but we should not forget it. And also, we typically rather get multi-field rather than single field, and we also have to cope with this. So there's still a few things to work, obviously, but... Okay, so within such a string theory realization, let's go back for a second to these solutions I mentioned. So we would like, for instance, to get a de Sitter minimum or vacuum. So this is really a cosmological constant. As we know, this is difficult, actually, from string theory, to have a well-controlled example. So there are many attempts, and it's great that there are attempts about it, but as we know, it's, for now, difficult. Another option is a de Sitter maximum. This is slightly different because for some time this is a cosmological constant, but at some point the quantum fluctuation which will push you away from the maximum, and so then you will start rolling down your potential. So this is a de Sitter maximum is a kind really of mixing between cosmological constant and quintessence scenario. That's also appealing a priori for what we want to do. But it's also difficult to realize, even though in the last minute of the talk, I will try to present an example. And the last thing is quintessence, so just slope. And there's one potential that we really like in string theory, which is the exponential potential, because we typically go to the field space asymptotics, where we have a good control on the model, and that's typically what we get. That's another question. Is this okay with observations? I'll talk about this too. So the plan of the talk is, first I want to talk of quintessence in general and how observations are done. And in 1 minute I will talk about this, and in 1 minute I'll talk about this, the string theory realizations. All right, let's get started. So once again, I take this type of model with matter and radiation and the FLRW metric. Let me remind you there's this Hubble parameter h, which is given by this ratio here, and this is positive because we consider an expanding universe. So you have to solve the differential equations. The first equation is the first Friedmann equation, which is given by this. 3h squared is given by the sum of the energy densities, and as you probably know, radiation goes as a to the minus 4, matter to a to the minus 3. And dark energy for us will be the scalar contribution, which is given by the sum of kinetic energy and potential. There's a way to rewrite this equation, which is simply that you divide by 3h squared, and so then you get that the sum of these omegas is given by 1, and this gives you the various proportions of the energy densities in the universe. As we know, today, dark energy is roughly 70%, and matter is about 30%, and radiation is very small. Those values are pretty much model independent, actually. Whatever model you take, you get more or less always the same values. So we're going to use these fiducial values for the whole talk. Okay, so that's one equation. Now, if you consider lambda CDM as a model, it means that there's no kinetic energy and you sit at the extremum of a potential, and therefore that's all you have. This is the only equation you need to solve. In other words, in that case, the solution is fully determined. There's no other initial condition to fix or anything. And in particular, you get right away the solution, which gives you this well-known evolution of the omegas. You get successive phases of first radiation domination, then matter domination, and then the rise of dark energy today. Today is this axis here. And this certainly agrees with observations. Now let's do the same, but for quintessence. So for quintessence, phi dot is not 0. And so you need further initial conditions if you want to solve the equations. So you need in particular to fix as an initial condition the value of this thing, which amounts to fix the value of W either today or at some point in time. So note that there are different possible solutions, different possible evolutions and history of your universe, depending on which initial condition you take. That's an important point. And so you need to fine-tune this initial condition if you want to get something which looks like our universe, if you want to get the successive phases I talked about. So for instance, if I take the exponential quintessence as a potential with this rate, I fine-tune the W0 today to this value, and in that case, I'm able to get a solution which gives me, indeed, radiation domination, matter domination, and dark energy. But if I take a different value, I will not get radiation domination. This will be very difficult. There's one big difference here in this plot with lambda CDM, which is that there's an additional initial phase here, which is kination, where the kinetic energy dominates. I don't have time in this talk to comment about this, but this is a feature we should remember. Okay, good. So I solved my differential equations. I have some evolution for my universe, which looks pretty reasonable. And now what is the evolution of W for such a solution, right? And that's what I want to know to compare to the observations. So let's do this. I remind you that for lambda CDM, W is -1, but for quintessence, it's given by this thing here. So in terms of E-folds, this is the result. This is the W I get for this solution. Okay? So this is W. So first thing is it varies a lot. It's not -1 all along. So there's a big difference. Okay? So it starts with an initial kination phase as I said, I don't have time to comment about this, but this gives you W equal 1. Then you go to W equal -1 during matter domination, and then it varies here. And then this is the future, but future we will not be alive to observe it, so we don't really care about this. So what is important is that it's -1 and then the recent variation. So you can see that if I just focus on that period here, this is extremely similar to lambda CDM, right? Because it's almost -1 all along, except recently, which makes it, in my opinion, very difficult to distinguish from lambda CDM. That's why I think it's difficult. Yes? Yeah, there would be a lot to discuss about it. I think I don't have time, but there are certainly bounds. It all depends how you patch this to what was before, inflation, reheating, and so on. I think there's quite some options there. Yeah. Yeah, yeah. Yeah, so if you change W0, you don't get this curve to start with. So that you should keep. But this rather depends on which scalar potential you take. The question you're asking depends on which scalar potential you take. This can vary a bit indeed. I'll come back to this. Yeah. So it was this, I'm always using that exponential I told about, but for all exponential, it's very similar anyway. Yeah. No, it doesn't need to be. It's just that initially kinetic energy is dominating, and so this gives you +1, and afterwards potential is dominating, and so you get -1. Yeah. Well, you can just understand that initially you have a lot of kinetic energy, so that dominates, and after a while this goes down to 0, and yeah. -6, yeah, yeah. Yeah, yeah, yeah. Yeah. Yeah, that is a good question. I'm currently studying this to try to understand how this is done. This is numerical results. Yeah, yeah, yeah. To some extent, because as I said, this fixes the fact you get radiation domination. If you tune further this initial condition, want to increase the initial energy a bit or something, you can change a bit the duration of this period. That has one effect. It's not entirely clear to me. Yeah, this is really work in progress, but yeah. Maybe, yeah, yeah. Yeah. Yes. That's a good observation. Yeah, let's try to prove this analytically together. Yes. But I agree. That's what we observe numerically. Yes. Yes. So I'm going to go right now to what they measure. You'll see that it's fairly close to this, actually, what they measure. Okay, so that's what we get from this simple exponential potential. All exponential potentials give you similar plots, only the recent part changes a bit. Yeah. Okay, so let me emphasize that there's this region with -1, and another explanation for this, and I think this is very important, is that in the whole past, actually, there is super high Hubble friction. And that's something we often forget about. There's a super high Hubble friction, and therefore, even if I'm on an exponential, I can have my field there stuck by Hubble radiation, Hubble friction, not rolling down, even though I'm on a slope, right? So And so this is also, that's another way to view this, at least for this part here, that the Hubble friction is very high. And finally, when you reach here, it starts lowering and your field gets freed and can roll again. But I think Hubble friction is important. You can also view this if you plot the profile of the field itself. This is the initial kination where the field is rolling. And then it's completely frozen all along, and very recently it starts moving again. So I think this is important because, for instance, this questions the need of moduli stabilization, right? So do we need to stabilize moduli here? Not really, because the field is just not moving, it's constant. So that's something to keep in mind. Yes? Which of do? Yeah. Yeah, I'm sorry, I didn't want to take time on this kination phase, so I'm not explaining much about it. As I said, before this, you need to have inflation at some point, and then you need to have reheating. So you need to patch all this past thing to this kination phase. And it's very model dependent how you do this. So it's not even clear there is an initial kination phase because it depends, how you patch it to the rest. So, but we might use it for purposes, as you say, maybe. Here. Yeah, you're right. There's another option, which is that the fill goes up and goes like this. Yeah, okay. This depends on the sign of your initial spit. Here I just plot one option, but there's always the other option. Well, not always, but sorry. No, it's not important at all. Yeah. Okay, good. Now let's go to observations and see what these guys have to say. So I plug here again the same W evolution. Observations want to discuss W in terms of the scale factor and not in terms of e-folds. So first we have to convert to this. So first let me just zoom to this region, because anyway the observations are only done until very recently. So they don't see at all, or the beginning at all. So we can just zoom in here, which is this curve here. Then I transform my n into an A, which is just an exponential. It gives me that curve for W in terms of A. So this is the same curve, but just expressed differently. So today is A equal 1. The thing is essentially growing. And when A was extremely small, at some point it goes up. But you see, this whole going up is really all packed here because it's due to this exponential versus... Okay, so now that's this curve we're interested in. Okay, let's take this curve. Now, what the observation people do is that they use this CPL or W0WA parametrization. So they use a linear approximation for W in terms of A, which is I take a constant and then there's hey, so I have a slope, and yeah, it's a linear approximation. It's like the justification for this is that it's like a Taylor expansion around the value today, basically. So if I take my curve, I want to make it a line, I can just do a best fit. That's what I do. And, well, it doesn't look too bad, actually, as a parametrization. So I do this between these values because this is up to redshift 4. This is where the observations go. And so I do the best fit for my curve of the exponential, and these are the values I get. I get a constant today, and I get a certain slope. Okay, and that's what I can compare to the observations. That's what can be compared. Yeah. Yes. Yes. No, that's not exactly true, because my W is really the W for the dark energy part. It's not the complete W of everybody. No, I don't think so. They also managed to distinguish the two things. Yeah, and they also give you results about W dark energy alone, which has to be -1 if it's, that's one way. No, they're not the same. They're not the same. If the dark energy is -1, oops, they're not the same. Because you need to multiply by the 70% thing. So it gives you a different value. I mean, the difference between the two things you're talking about is this 70%. So they're not the same, and they do measure dark energy alone, not everybody together. Okay, so that's what I get. In the paper with Tim and Susha and Yvonne and Dimitrios, we actually did this for various rates of the exponential potential. So square root of 3 is what I was using so far, but we've done the same work for different rates, basically. Okay, we get pairs on numbers. That's what we get. Now we compare to observations. That's what the observations say. So the observations propose different pairs of numbers. They propose 3 of them because they have different data sets depending on which supernova data you use, and etc. There are also error bars, so I'm not showing everything, but it's just to give you a taste. So that's the numbers you can find in their papers. As you can see, there's none of these pairs, even with the error bars, which fits any of these pairs, right? Actually, the WA, the slope they get, the WA here, is way bigger than what we typically get. So essentially, this excludes exponential quintessence. If we want to fit to this data, exponential quintessence doesn't make it. So there are 2 ways. Either it's a different scalar potential, or these observational values may evolve a bit in the coming years, and then we can check again this table. Yes. So Susha and Yvonne actually also tried to get a more precise bound. They claim that the bound is lambda is 0.7. But I think even with this, you don't really fit the DESI data properly. Okay. Yeah, I'm sorry, I'm not showing them, but it doesn't help you in solving the problem. They're still pretty large, but. Expansion. Yeah, or that they try each potential separately, basically. Yeah. It's just to get a sample. It's just to get a sample of values. But I mean, the evolution is pretty clear, right? I mean, this goes down in absolute value. This goes up in absolute value. I mean, no. Absolutely, yeah. It's just yeah, absolutely. No, not really, because lambda being very small, you're close to -1, but WA is very small too. And here, WA is huge. It's not at all within the error bars. I mean, I'm not showing the error bars, but... Sorry. Good. No, this is for a varying thing. Yeah, okay, good. Maybe I shouldn't have shown this. Yeah, sorry. This is when you plug in a varying quintessence model. I mean, this model, actually. Well, you could also do that, sure. Yeah. At first sight, it seems difficult to make it work, but yeah, yes. Yeah, there is a correlation. it's not straightforward to see, but we can understand this, yes. Yeah, in some sense, yes. Magdalena. Yeah, so this is because they use different data sets of observations with, in particular, they need supernovas at some points, and they use different data sets of it. And unfortunately, it doesn't really give the same value. We would prefer them to have all the same value. They're also not very happy themselves about it. But there are also error bars, which, you know, makes it more or less consistent. Yeah, but here I'm just showing the central values, just to give a taste on the values. Yes. So if you rather from the start use lambda CDM and not this model, then and you compare the two, there's a 3 sigma between the two things indeed. Yes. I'm not going to discuss other potentials, no. Because I'm out of time already. No, I mean, we should try other potentials, and I invite everybody in the room to try other potentials, absolutely. Very quickly, I say very quickly 2 things. Okay, so that's what we should all do in the coming years, and try as many string models as we can, I think. We did this for exponential quintessence. So if you want to know anything about exponential quintessence, you can look at this paper, because we studied it in all possible details, even though it's an old story, but I think we did lots. Irene is not happy, so I'm gonna show it. This is a phase space with all the fixed points that some of you know, and this is cosmological solutions in the phase space. These are, well, just to show you. Lambda has to be smaller than square root of 3 if you want anything realistic. That's also something we get. That's an important result. Lambda has to be smaller than square root 3. Okay, there is some string theory realization in this paper, if you're interested. Okay. Another option is de Sitter. We also have a good attempt for classical de Sitter in this paper with a parametric control. So we have a parameter which makes the classicality as good as we want, a bit as in DGKT. At least that's the hope that we have, and it seems we have this scaling freedom. So that's an interesting example to look at. And the connection to what I said before is that your potential is like this. We have 22 fields. Among the 22 fields, there's 1 tachyon, and all the rest is okay. So you can, this is stabilized, metastable, and you can start rolling down from your de Sitter here downwards, hoping that when you roll down, you do the quintessence. And maybe this matches the observations. So that's another example, a maximum de Sitter, as I said in the introduction, that could maybe do the job. That would be a string theory realization. And I will stop here. So this is the summary. I think this is really important, understanding the evolution of W in terms of A. This is soon observationally constrained. Hubble friction is very important. I think we really underestimated this in string Fino and Swampland discussions. And we want to do string theory realizations. And one thing which is very important is we need to include matter. This is 30% of our universe. We never talk about matter. We need to have the matter at the same time as the rest. This is very important. Thank you.